Okay, so let's start the class. Just mute yourself. If you have questions, you can ask. So let's look at equilibrium of forces. Now, let's observe. How do we know when a body is in equilibrium? How do we know when a body is in equilibrium? Don't worry, if you're unable to catch up with anything I'm writing, I'll send the notes to you. So what you're just going to do in this class is just to pay maximum attention and avoid any form of distraction. Okay, let's commence. So when do we say a body is at equilibrium? Now pay attention. It's possible that we have a body and that body is being acted upon by external forces. That body is being acted upon by external what? External forces. Now pay attention. If we find the net force of all those external force and we see that, oh, the net force is 0, that is the net force of all those external forces acting on the body is equal to what? 0. Therefore, we say that what the body is at equilibrium. So when a body is at equilibrium, the net force, or you call it resultant force, acting on the body will just be equal to what? 0. And pay attention, don't forget, everyone knows this formula, F equal to ma. If I say our net force equal to mass times acceleration, if my net force is equal to 0, according to equilibrium, I'll have 0 equal to ma. If I divide both sides by the masses, I'll have 0 divided by the mass, I have 0. So my acceleration equal to 0. It means that when a body is at equilibrium, the net force is 0. Also, the acceleration on the body is also equal to what? 0. Exactly, 0. So 0 Newton, 0 meter per second square. So if a body is at equilibrium, the body will not accelerate. The body will not accelerate. Good. I believe that is clear. Next, equilibrium is divided into 2. We have 2 types. One of them is called static equilibrium. One of them is called static equilibrium. And the other one is called dynamic equilibrium. The other one is called dynamic equilibrium. The other one, we call it dynamic equilibrium. So what is static equilibrium? From the one static, if we say something is static, it means that what? That body is not what? Is not moving. Are we together? So pay attention. When a body is at static equilibrium, what do we say? We say that same condition, the net force is 0. We already know that one. The net force is 0. And at the same time, body is at rest. The body is at rest. Good. The body is at rest. Nice. The body is at rest. Good. So when the body is at rest here, it's at what? Static equilibrium. Also, the net force is 0. So when do we say a body is at dynamic equilibrium? Now, pay attention. The word static means it is not moving. That is why we say the body is at rest. Remember, when the body is at rest, what do we say? The initial velocity is 0. It's not moving. Good. But dynamic equilibrium, the body is at equilibrium, but it is moving. It is what? Moving. Now, pay attention. When a body is at dynamic equilibrium, just pay attention. When a body is at dynamic equilibrium, what do we say? Pay attention. It means that the body is what? Is moving. The body is moving. Moving with what? Moving with uniform velocity. If you don't want to use the word uniform, you can use constant velocity. Constant what? Velocity. Good. When the body is at dynamic equilibrium, the body is moving with uniform or constant what? Velocity. Now pay attention. If a body is moving, let me say, in a straight line, that is, I mean, the body is not rotating now. The body is moving, let me say, in a straight line, like translational motion. Then we use this word uniform or constant velocity. But what of if the body is moving in a circular path? What do we say? So for that case, we don't say this. For that case, we say that the body is moving with what? Moving with uniform angular velocity. Uniform angular velocity, exactly. Nice. Please take note of all those facts. Very, very important. Take note of how we re-explain again for you to get it well. Static equilibrium, the body is at rest, it is not moving. Dynamic equilibrium, it is moving. So it's either moving with what? Constant velocity or uniform velocity. That is, what's not uniform velocity? The velocity is not changing. It's the same all through. And also, yeah, it's moving at a what? Constant angular velocity. We use the word angular when the body is moving in a circular path. Nice. Okay, so that is it. And pay attention to something. In our secondary school, when we're still SS1, when we're doing equation of motion, they will tell you that when you hear that, whenever you have anything like uniform velocity, or whenever you have anything like constant velocity, whenever velocity is not changing, take note that acceleration is zero. Now, let me give you an example. If you want to board a bus, or let me say a bike, or you want to enter any form of transportation, pay attention that before the bike start moving, it means that the bike was not moving initially. You boarded the bike and you want to start moving. You observe that by the time the bike man start moving the bike, there's a way your body responds to that acceleration. If you observe, you jerk backward. For those that always entered means of transportation, you understand what I'm saying. So that point where you jerk backward, you observe that yes, this body is just accelerating. But it not get to a point whereby the velocity will not change. The bike will just be going straight like that, or the bus, the velocity is not changing. That's what we call what? Constant uniform velocity, and it's not accelerating. So that's why you are able to maintain a kind of fixed position in the bus, and that's that. So whenever you hear that any object is moving with uniform velocity, there is no acceleration. Acceleration is zero, and that is it. Now, let us now move on. What we now want to be looking at is what we call moment of a force. Moment of a force. Moment of a force. Yeah. Moment of a force. Now, what is moment? Moment is just talking about the turning effect. Moment is what? The turning effect produced. The turning effect produced by a force. The turning effect produced by a force is what we call what? Moment. And for calculation's sake, what's the formula for calculating moment? Now pay attention. Moment is equal to, pay attention to the formula, force multiplied by perpendicular distance. Force multiplied by perpendicular distance. That is, we find the force and the perpendicular distance. Don't worry, I'll tell you how to do for all this. So what's the unit of moment? Force is Newton. The unit, look at the units. The force is Newton and the distance is what? Is meter. So this is Newton meter. That is the unit of moment. Now pay attention to something. Pay attention to something that to find moment, please take note of the keyword. The force and the distance have to be perpendicular. We don't just use any other distance. They have to be perpendicular. Now, the question is this. Some people are still joining. Wow. Okay, let's go. Let's move on. Now, the thing is this. If the force and the distance are not perpendicular, what of if they are parallel? Remember, to find moments, your force and your distance must, don't worry, I'll tell you how to find all this. Just follow the explanation. Okay, now the force and the distance have to be perpendicular. Now, they are not perpendicular. If they are not parallel, what will happen? Now pay attention. If the force and the distance are parallel, don't worry, let me use this simple word. I'll tell you what I mean by this. That is, if they are parallel or if the line of action coincides with that point where you want to find your moment, therefore, your moment is equal to 0. Your moment is equal to 0 Newton meter. Don't worry, you understand this by the time you are solving question. So just take note of those points. Good. Just take note of this point, and that is that for that. Okay. So that's how to find moment. Force times what? Perpendicular what? Distance. Okay, pay attention. Now, what do we now call torque? What do we call what? Torque. you represent that with tau, this Greek letter tau. Now, what do we call torque? If I'm done discussing torque and everything, then we'll solve question on moment. Now, what do we call torque? I'm coming. Let me admit someone. Now, pay attention. Torque is also the same thing as moment, but let me discuss something. There is something we call couple. What's the couple? Now, pay attention. Observe this system. Let me look at the steering of a car. And observe that when you are handling a steering, one hand will be at this side, another hand will be at this side. But you observe, one hand can be pushing the steering this way. So there's a force going this way. Another hand can be pushing the steering this way, and there's another force going this way. The force has the same magnitude. Now, if you observe, what happens in a couple? You see these two forces will produce what we call turning effects. We produce what we call what? Turning effects, exactly. Because if you observe, as the person is pushing the steering this way, the body will be what? The steering will be rotating out together to be what? It will be rotating. Nice. So this system is what we call what? A couple, a steering. Even your tap. Some of you that have tap at home, if you observe, how do you undo your tap like this? You know, what do? You put your hand here and you observe that one will be moving this way, the other one will be moving what? This way. The forces are parallel. You can see. So the effect of these forces on this system will be rotation. It will be causing this thing to rotate. Also your door handle and so on like that. So what do we now call a couple? It's very easy. If you can draw this diagram, you can define a couple. A couple is a system of two forces. Those two forces are what? Equal in magnitude. They are opposite in direction and they are parallel. That's what we call what? Couple. I'll define that again. It's very, very simple. Don't worry, this video is being recorded. You can watch it over and over. Okay, what do we call couple? It's very easy. We say that what a couple is the combination of two parallel, equal, and opposite forces. Combination of what? Two equal, parallel, and what? Opposite forces. Whose line of action do not coincide. Yes, their line of action do not, it did not join together. Exactly. So they are parallel to each other. You see, if I draw a line here, you see that this force here is parallel to this force here. Also, they are opposite in direction. What do you mean by that? One force is going here, another force is going what? Down. So they are opposite in direction. That is what we call what? A couple. Now, what do we now call torque? Torque is now what? The moment of a couple. Okay. Torque is the what? Is the moment of a couple. So that's what? Moment of a couple. So moments of a couple is what we call what? Torque. Yeah. So the way we find torque is easy. So we just simply our torque, or see, you can say moment of a couple, or you say you want to find torque, whichever way. It's the same formula. So how do we calculate it? We just say the force, one of these force multiplied by the distance between these two forces. Okay, take one of these force and multiply by the distance between the two forces. If you observe that, you see that the force and the distance, you can see that they are perpendicular. You can see they are perpendicular. Exactly. That's how we find moment. They must be perpendicular. So force times what? Perpendicular distance. That's how we calculate what? Torque. Good. So that's that for that. Okay, please, do anyone have question? Do you have question before I move on? Is there any question? You can mute yourself. So let's see if you are following. Okay. Anyone have question? Okay. Can you mute your mic and let me know if you have question? Okay. If there's no question, so we can move on then. All right. Okay. There's no question. All right. Okay, let's move on. So let's look at some questions. Some simple questions. Okay. Okay, let's look at some simple questions. Everybody observe. Look at this. If you have a question like this, Okay. If you have, let me say this force going here is 8 Newton. And then you have a point here. Let me say point O. And the distance between these 2 points is, let me say, you have what? 5 meters, for example. Now, see what we have. Please pay attention. If they ask you to find the moment of force 8 Newton about point O. About point what? Point O. Now, please pay attention to this. It's very, very simple. Let's start with a simple question. Now, please pay attention. How do we find the moment of this force 8 Newton about point O? It's very simple. Now, see what you are going to do here. You see, pay attention that moment is equal to force times perpendicular distance. And if you observe, look at my force here. Now, the question is this. What is the distance of 8 Newton? Or I would say, what distance of the line of action of this force and this point O? Now, please pay attention. Someone might want to say, okay, this is the distance. I'm coming. Some might want to say, okay, this distance of 8 Newton to this one. But do you know why the person is wrong? This is not a perpendicular distance. Exactly. But look at it. Pay attention. This is how you are going to get it. Just draw a broken line along the line of action of your 8 Newton, because there's a principle in mechanics. That principle is that the line of action of a force is continuous. If they draw a force for you like this, you can extend it. There's no problem. You are correct. So extend your line of action of force and check. Now look at any line that is perpendicular. Now check the one that is, look at this distance there. Now look at line of action of your force. Now what distance from this point to your point O? If you observe this distance, you see that what they are perpendicular. Perpendicular means that the angle between them is 90 degrees. So the line of action of your force, this is it, and this is what? Perpendicular distance. And that perpendicular distance is what? 5 meters. So my force is 8 Newton, then multiplied by my distance is what? 5 meters. And what is 8 times 5? That is what? 40 Newton meter. That is the moment. That's the moment. A very simple question. Now, let us make the question a little bit different from this. Okay, look at another question here. This is point P. This distance is 12 meters. And this is what? 30 degrees. This is 30 degrees. And you have 10 newtons. Okay. They said calculate the moment. Calculate the moment of the force 10 Newton about point P. About point P. So that's it. About point P. So that's it. Okay. So pay attention, look at it. I want to calculate the moment of this force about this point P. So what are we going to do now? Pay attention. This is a little bit different. Now see. Don't forget that this is the line of action of my force. Just a straight line that passes through this. And you want to find the moment of that force from this point. Now, this is what you are going to do. See, I cannot say, let me draw a line from here to P. No, you can't do that. It will not make sense. So this is what you are going to do. See, remember that this broken line you see here is perpendicular to this 10 Newton. So what you are going to do is this. You are going to find what this broken line is, what this horizontal line. You are going to find it. How will you find it? Pay attention. You are going to resolve this force to the horizontal. Remember, check my force here is vertical. So you resolve this point P, resolve it to this horizontal so that it will now be perpendicular to your 10 Newton. So the question is this: how do I resolve my point P to this point? Now, let me just tell you something. Let me just tell you a very short way to do it. See, assuming that, let me say you are completing your triangle, assuming, you see, wherever your angle is facing, wherever that side that is opposite your angle, you are going to use, what will you use with it? You are going to use sine. Because if you look at your SOHCAHTOA, out of your cos and sine, the one that have opposite is your sine. So wherever is opposite to your angle, you are going to use sine theta. Okay? You are going to use your sine theta. So if I want to resolve, so I'm going to resolve this line here to the what? To the horizontal now. Now, but check. If I want to resolve this thing now, what do I do? Pay attention. I say wherever your angle is facing, you are going to use sine. So this part is 12 sine theta. This part is what? 12 sine theta. And this other part should be what? 12 cos theta. Why am I using sine here? Wherever my angle is facing, I will use sine with it. Okay, good. But remember, I don't need this. Please give me some seconds. Remember, this is the part I needed because this is the line that is perpendicular to this force, okay? So I'm using this line. Please don't forget, this is the line that is perpendicular to this force, exactly. So, but if you want to resolve and you complete a triangle, wherever your angle is facing, you will use sine, and the other part you use what? Cos. Good. So therefore, the moment that I'm looking for is equal to, remember, the force times perpendicular distance. Now check, what is my force here? My force here is 10 Newton times what is my distance? 12 cos theta, and my theta is 30 degrees. That's 12 cos 30 degrees. So let's go on with our calculation. So I have 10 times 12 times what is cos 30? Cos 30 is square root of 3 over 2. That's mathematics solved. Square root of 3 over 2. That's cos 30. If it is cos 60, it's 1 over 2. So 2 here 1. 2 in 12 will give me 6. So 10 times 6 is 60. So I have 60 root 30, good 3 Newton meter. So that is my answer. That is my answer. So that's how to find what? Moment. That is how to find moment. That's how to find moment. Okay. That's how to find moment. Some parts still joining. Okay. Okay. All right, so that's how to find moments. Okay, so let's continue with our explanation. Okay, pay attention to something. Now, this is, let's continue. If you are unable to catch up with the notes, it will be sent to you. All right, now let's go. So look at something like this. You see, okay, Joy, do you have a question? Unmute yourself.
Yes,
Okay.
sir. I have a question, sir.
Okay,
So, what
encore.
if whereby we are asked to leave it in a short form?
Yes. This is what we call short form. I left it in a short form already. This is a short form. That is where, if I don't want to leave it, pay attention, Joy. If I don't want to leave it in short form, I will have 12 times 12 times cos 30. If you press calculator, you'll be having 0.866. And this is not a short form. Here you're using calculator. But if I have to use short form, you are going to just note something. You will note this thing, that sine 30 is equals to half, cos 30 is equals to what? Square root of 3 over 2. Then sine 60 is equals to square root of 3 over 2. Then cos 60 equal to what? Half. You can know this. So this is what we call short form. Okay, is that clear?
Yes, sir.
Can you hear me? Exactly, that's that. Good.
Yes, sir.
Okay, good, nice. Okay. Okay, that's how to find moments. Okay, let's move on to the next page. Okay, now pay attention. So what we now want to look at we want to look at the equilibrium of system of forces. Everybody pay attention. This is, you see this line? We all know this laboratory, we all know this particular instrument I'm drawing in the lab. We use it for mechanics a lot. It is called a meter rule. It is called what? A meter rule. Now, a meter rule is used for measuring length. Okay, a uniform meter rule is from what 0 to what 100 centimeter, and that is 1 meter. Good. Or you say, or it's 1 meter. Now pay attention. You see, please, that candidate, please mute yourself, please mute yourself. Yeah. So there's this other one called knife edge. We call this what? The knife edge. Now look at this system. Pay attention. A meter rule is being balanced on what? On a knife edge. Now pay attention. Let's assume, please, let's assume that we have a force at this side. Pay attention. This part is very, very important. Let's assume we have a force here. We have a force here. We have a force here. We have, let me say, these are straight ones. They are not curved. We have some force here, and we have another force here. Now pay attention. So let me say this is F1, and this one here is F2. This force F2. So let's say this force F3, and this force F4. Now, you see, pay attention. Note that there's one thing you need to know. This is the point where we will be taking moment. Because this is the point where this meter rule can, can move, can kind of move over. So this is where we are picking our moments from. This is where we are picking our moments from this knife edge. Now pay attention to something. Let's say the distance of this point to this point, the perpendicular distance of this force to this knife edge, let me call that x1. Let me call that x1. And the distance from this our point to this force F2, I will call that what? X2. You'll be able to find the distance, don't worry. This one from here to here, let me call the distance x3. While from here to here, let me call the distance x4. Now pay attention. No, don't forget, I believe that as we are all in this class, we are sitting on something. You see, if you are sitting on something, your weight is going downward. Your weight is coming downward. But in this example, I don't want to consider the weight or mass of anything. Let me just use this simple example. I don't need a simple example. Now let's go. Now, let's ask ourselves a question. My first question is this. What type of moments will F1 create on this system? Please pay attention. You understand something now. See, if a boy dragging this meter rule upward this way, some person joining the class thing now, and that is distracting my class a little. Okay, let's go. Look at this force here now, the way it's moving this way. If someone is dragging the force this way, if you remember, if you just observe this system, imagine the system will be moving this way. Yes. Look at your fixed points here. Your system, if you are dragging this force the way it is like this, the system will be moving this way. And if you look at this type of direction, is this clockwise or anti-clockwise? Is this clockwise or anti-clockwise? Check it out.
Clockwise.
Clockwise, thank you. So this force F1 will create what we call clockwise moments. Clockwise moments, exactly. That is clockwise turning effects. That's the meaning. Okay, let's look at F2. The way F2 will be, if someone drag this thing now, and you observe that the thing is sitting on this, it will be moving this way. And what type of moment is this one? Everybody check. Look at this. Look at where it's moving. What type of movement is this? Is it clockwise or anti-clockwise? Look at where it's moving. That's what. Who can tell us?
Clockwise, anti-clockwise.
Exactly, anti-clockwise. If someone want to blow grammar for you, they'll say counterclockwise. But anyhow, all of them are the same. Anti-clockwise movements. Now, because before you start solving a question like this, you have to know what type of moment is this, are they creating, then you know what to do. Now, let's go. Look at this F3 now. Let me say someone come to drag this, you know it's going to move this way. And look at F3. What is it creating? Clockwise or anti-clockwise? Look at F3. Be careful for your answer. Yeah? Who will tell us?
Anti-clockwise.
Exactly, anti-clockwise. Nice. So we have anti-clockwise moment. And assuming you are dragging this now, what type of moment is this? Someone should tell us again. Look at this F4. What type of moment is this? Clockwise. Thank you. Clockwise moment. Yes, clockwise moment. So I have clockwise moments here. Now, there's a principle. There's a principle we call principle of moments. Yes, in advanced level, we call it Varigon's theorem. Now, what's that principle telling us? It's telling us that what? Look at this system. It's telling us that the sum of clockwise moment is equal to the sum, this sign means sum, of anti-clockwise moment. It's equal to this sum of anti-clockwise moment. That is it. The sum of clockwise moment is equal to what? The sum of anti-clockwise moment. Yeah. Okay, if they ask you that, what type of forces are these? You see, this system is what we call a system of parallel coplanar force. Pay attention. Parallel coplanar force, if you observe, the forces are parallel. Check. Look at where this is moving. Parallel, their line of action can never meet. So this is a system of parallel coplanar force. Coplanar means that when they act on one plane, they act on the same plane, exactly. And one of their conditions is that sum of clockwise moment is equal to sum of anti-clockwise moment. Another condition is, pay attention, whenever you are dealing with this system, you will say clockwise moment equal anti-clockwise moment. Also, you will say the sum of upward forces is equal to the sum of what? Downward forces. Okay? So what do we see? What are the upward forces? Who can tell us? What are the upward forces? What are those forces that are going upward? What are those forces that are pointing upward? Who can tell us? Do you see any force pointing upward? Let someone tell us.
F1 and F2.
F1 and F2. That so it says F1 plus F2. They are the upward force. Then equal to what? What are the downward forces? F3 and F4. So F3 plus F4. Exactly. F3 plus F4. Good. So these are the two ways we used to solve a system like this. Now, let's go back to that first one. Sum of clockwise moments equals sum of anti-clockwise moments. Okay, let's go back to that first one. Let me keep this one here. Okay. Now, please pay attention. Don't forget those forces that are creating clockwise moment. Now, let's not look at clockwise moment. Let's look at force F1. Let's look at force F1. And let's look at force, which other one is creating clockwise moment? F4. Now, how do we find the sum of clockwise moments? Please pay attention. How do we find the sum of clockwise moments? Now, moment is force times distance. So the moment of this force creating clockwise moment is F1 times this distance, x1. That is distance from this point where we are picking our moments from. Okay? That is this our what? This is our reference point. Let me call that point O, where we are picking our moments from. Good. So my clockwise moment, so I'll first pick F1 times distance x1. So this one is creating clockwise moment. Now, another body creating clockwise moment again is this F4. So how do we calculate moment of this F4? It's simple, just the same way we have been calculating. F4, distance of this force to this point where we are picking moment is what? X4. Exactly. This is our clockwise moment. Exactly. So this is the moment of this force, this here, and the moment of this force creating clockwise moment, this is it. That's it. Now, equal to sum of anti-clockwise moments. What's our anti-clockwise moment? Which forces are those one creating anti-clockwise moments? F2 and F3. Good. Now, let us now find moment of F2. The same way to find moments till we finish this topic. Force times perpendicular distance. Our force is F2, and the perpendicular distance of this force to this one is what? Who knows the distance?
X2.
X2, exactly. So we say what? Times X2, and that is it. And lastly, The next one we are finding its anticlockwise moment. Look at this system. The other force creating anticlockwise moment is this force F3. Are we together? Is this force what? F3. So what's the moment of this force F3? So you add it with this. So I have F3 times what is the distance of force F3 to this point, exactly, X what? X3, exactly. You see this point, they call it pivot. If you just head to the pivot, good. So that's how to find what? The moment. Now, since we have learned all this, let us now look at some questions. Let us now look at some interesting questions. Okay, yes, let us look at some interesting questions. Let me just take one and solve, then we move on to the next. Okay, my first interesting question is this. Look at this system. Pay attention. Look at this system. It's very simple. You can just understand the concept. You are not just to cram. Don't just cram at all. Just understand the concept. Then you get it. Okay, look at what we have here. So we have 10 newtons. We have 10 newtons. And we have 0.25 meter. Now, look at this thing. Look at this figure. Yeah, they ask you to calculate the moment. Calculate the moment of the couple. This question can come different. You can say calculate the torque, calculate the couple. Just know. But you pay attention. Without them telling you it is a couple, everybody, you should know this is a couple. How? We have two equal forces. They are opposite in direction. Also, they are parallel. This is what we call a couple. So how do you find moment of a couple? How do we do it? We just, okay, the moment of a couple, solution. The moment of a couple, and that is torque, torque, equals to force times distance. And please pay attention. One of the wrong solving that student can do is to say, okay, how many forces do I have? 10 plus 10, 20. No. We don't do that. Okay, we don't do that. We will just pick one of the force, 10. You know, I have 10. Just pick one of them, 10. Then times what distance between them? 0.25 meter. The answer is 2.5 Newton meter. That is the answer. That is the answer. That is the answer. So that is a couple. That is a couple. As simple as that. Okay, so let us look at another question. A very simple question. Okay, let's look at this question. I think it's the third question only. So, okay, next question. Okay. Please, my next class, let's endeavor to join the class very early, please. Please, let's endeavor to join the class very early so there will be no distraction. So let's look at this question. A meter rule of mass 0.42 kg is balanced. A meter rule of this mass is balanced at 60 centimeter mark. Don't worry, you understand this very well. When a mass M is placed at 90 centimeter mark. Full stop. Chocolate the value of M. Chocolate the value of M. As simple as that. If you need options, do you need options? I don't think you need it. Let us just solve the question. Solution. Now, look at it too. Let's get the question. A uniform meter rule. If you hear the word a uniform meter rule, it means that you have a meter rule that the length is what? 100 centimeter. That is, you have from 0 to 100 centimeter. That is the meaning. They said the uniform meter rule has a mass of 0.42 kg. Now, everybody pay maximum attention at this point. Now, there's something we call center of gravity. Center of gravity is that point where the weight of an object will act. Points where the weight of an object will act, okay? Now, look at this object now. The way this object is, I'm just having a straight line, which is this meter rule. The center of gravity or the center of mass of this meter rule, where the mass will be, where the weight should be, altogether is the center. That point where the weight should be will be the center, 50 centimeter. Because how do I get 50 centimeter? The what? The length, look at this thing, the length is 100. So half of 100 is 50. So this 50, this is my center of gravity. Don't forget, this is my center of gravity. So why is this thing needed? If they are telling you the mass of the meter rule or the weight of the meter rule, please, you have to put the weight at the center. Don't forget. So let's look at the question again. A uniform meter rule, that's 100 centimeter of mass 0.42 kg. So that's 0.42 kg. We are going to put it down here like this. 0.42 kg. Yes, that's it. It's balanced at 60 centimeter mark. Now, what is the 60 centimeter? Now, check. This place is 50. Therefore, this part should be what? Somewhere around this side will be what? 60 centimeter. So this point might be 60 centimeter. So they said that it is balanced. Check. It's balanced at 60 centimeter mark. When a mass M is balanced at 60 centimeter mark, what does that mean? It means that they put that knife edge. They put the knife edge here like this. Exactly. This is the knife edge. Exactly. So this is what if you do practical mechanics, this is what we use to balance. This is called the knife edge. Or some people call it pivot. So this is where it is being balanced. They said when a mass M is placed at 90 centimeter mark, where's our 90 centimeter? This 100, 90 centimeter will be somewhere here. Exactly. You cannot see my screen? Hello?
Yes.
Who else can see my screen? If you can see my screen, let me know.
Me.
You can see my
I
screen.
can't
Right?
see it though.
You can't. Wow.
No.
I'm coming. Let me reshare it again. Don't worry. Everything will be seen clearly when I send the video. Just don't worry. You will not miss anything. Both the notes, everything, the explanation, everything about the details of this meeting. You receive everything. Don't worry. Okay. Can you see my screen now? Can you just see some parts? Like, if you can see it, let me know.
Yes, I can see the screen here.
Okay, good.
I can see it, sir.
Nice, good. So let's continue. So I will explain again because some people were not able to see my screen. Now, see, they said a uniform meter rule of mass 0.42 kg. If they give you the mass of anything, come and put it at the center. That's the center of gravity. So the whole meter rule is 100 centimeter. So the center of gravity will be at the center, which is 50 centimeter. So I'll now come here and label that 0.42 kg. I'll put it here. In other words, it's balanced at 60 centimeter mark. This is what we normally use to balance the meter rule. This is what we call the knife edge. This is what we call the knife edge to balance it. So it is being balanced at 60 centimeter mark. Then I said, when a mass M is placed at 90 centimeter mark, so look at mass M here. So there's a mass here called mass M. They put mass M here like this. Good. At that 90 centimeter mark, they now ask us to chocolate the value of M. So this is what we want to get. This is what we want to get. Now, see the question now. So what do we now do? We apply what we call principle of moments. We apply what we call what? Principle of moment. Principle of moment. And what principle of moment is, and gentlemen, is what sum of what clockwise moments equal to what sum of what anti-clockwise moment. Now, if you observe this one, this 0.42 kg creates a clockwise moment. No, sorry, creates anti-clockwise moment. You know, the way it's moving like this. Why this one creates what clockwise moment exactly? All right, so we are picking our moment from this one. So you ask yourself, what the distance from here to here? The distance is 10 centimeter. And distance from here to here, the distance is what? 30 centimeter. Good. So solution, let me do my workings at this side. Okay, let's go. So we say clockwise moment equals. Now let us now, these are clockwise moments. So what is the force I'm having here? M times what the distance of this to this point. The distance is what? 30. And I don't have any other force again on that side. Then equal to, which one am I having at this side? 0.42 kg. Then times what is the distance of this 0.42 kg to this pivot? 10, exactly. So I'm looking for M. I'll divide both sides by 30. By 30. So what do I have here? 30, we cancel 30. So what do I have here? Check 0, cancel 0. So my M equals 0.42 kg divided by what? 3. So let's go. So let's divide. So 3 here, 1. 3 in 0.42. What do I give you? What did I give you? It's simple. You can do that without calculator. Please observe. See what you're going to do here. Just pick your 42 and divide it by 3. 3 here, 1. 3 in 4. 1 remainder 1. And 3 in 12 is what? 4. So it's like I'm having 14 as my answer. But remember that initially I have 0.42. And that was 2 decimal place. So put this on 2 decimal place. You have 0.14 kg. So that's the value of M, 0.14 kg. Or some of us can do it in some other ways without calculator. So let's learn to rely on ourselves without calculator. So that's the question. So that's that. So this is how we use principle of moment. Nice. So the next aspect that we are going to be going to is that the next aspect we are going to be looking at is, let's look at this. Let's look at Lami's theorem. Let's look at Lami's theorem. Let's look at Lami's theorem. Now, pay attention to this part. That there's something we call, look at this forces here. This is the logo of a car. Please give me a second. Okay. This is the logo of a car. Best car, you see this type of logo. Right? You see this kind of logo. I mean, is that right? So let me say this part is force F1, and this part is force F2, and this is what? Force F3. So let me say the angle facing force F1, the angle facing force F1, this is the angle here, and that's cot theta 1. The angle facing force F2, theta 2, and the angle facing force F3 is theta 3. So according to Lami's theorem, what do we do according to Lami's theorem? So you get to now, according to Lami's theorem, what do we do? We say what? F1 all over sine theta 1 is equal to F2 divided by what? Sine theta 2 is equals to what? F3 divided by what? Sine theta 3. So we just do 2 of them, and that's sufficient for us. We just do 2 of them, and that's sufficient. Don't worry, we have different theorems that we can use. So this is what we call Lami's theorem. Just hold it down. I'll solve a question to make it clearer. Okay, let's look at something like this also. Let's look at something like this. Okay. Let's look at this system. Theta. There's a force going along this side, and that's T, the tension. There's a force here, and I have the weight going downward. Now, please pay attention to this. Very, very important. Now, you see this particular question can be solved in 3 different ways. 3 different ways. But we always use the easiest of them all. Because me too, I like something that is easy. I don't like something that is hard. So I will use the simplest of them all. You can use Lamy's theorem if you like. If you like, you can use different ones to use. Now, the first one I would like to tell you about is what we call the triangle law. The triangle law of forces. If you want to use triangle law, how do you do it? Now, pay attention. I will represent this diagram with a triangle. I represent this diagram that you have in here in what? Triangle. Okay? I represent that in what? In a triangle. Okay, let's go. Everybody will observe. You will see that this particular weight is coming down. And remember, I told us that whenever we are dealing with this, we can always extend the line of action of the force like this. So my weight is coming down like this. Let me use straight line. My weight is coming down like this. So this is my weight. This is my weight. Then after that, look at my force, the way it's going. It's going in this direction. So I will write my force this way, going in this direction. And look at the way my tension is going, like this. So I will draw my tension like this. Exactly. Draw my tension like this. So check it out. This is the weight. Check that. So this is the weight coming downward. This is the weight coming downward. Also, look at the force going in this direction. So this is my force going in this direction. And look at my tension. See, going in this direction. So, and look at my theta. Everybody check. This theta here is the angle between the tension and the vertical. So the angle between this tension and the vertical is also theta. Then we now use mathematics to solve it to get whatever we want to get. So swap. And that is that. That's one of the ways you can use to solve it. Now, another way you can use to solve this, when we are solving question, all this will make total sense to you. Now, let's see. Another way you can use to solve this simple question you're looking at is using resolution of forces. That is, pay attention. You see, have it in your mind that when the body is at equilibrium like this, upward force equal downward force. The force on the right hand side is equal to the forces on the left hand side. That's it. That's the simplest way you can use and get it. I'll say it again. Force that is going upward, add all of them together, is equals to the total force that is going downward. That's one. Also, all my forces that you have to the left is equal to the sum of all the forces you have to the right, and that's it. But before you apply that law, there's something you are going to do to this guy. You know, this guy has some angle. So you are going to resolve this tension to the vertical and to the horizontal. Now pay attention. You see, complete this triangle. And let us use that thing I told you that time. I said, wherever your angle is facing, call that sign. Wherever your angle is facing, call that what? Sign. Don't forget. Wherever that side that is opposite to your angle, call it sign. So this is sine theta. This sine theta. And this other part that you have here, call it cos theta. See cos theta. And that's the easiest way. Complete your triangle. Wherever your theta faces, use sine theta. The other point is what? Cos theta. Wherever your theta faces, sine theta. Other theta. Now, what will not be the direction? Everybody pay attention. It's very, very simple. Now, if you observe this tension itself, please, if you observe this tension itself, the direction is away. The direction is away from this point. So therefore, this component also, their direction will also be away, like this. Will also be away. This one will go here, and this one will go here. They just have to just move away from this point here. So this is what we have. Oh yeah, now let us apply that short principle I said. I said all the forces you have to the top is equal to all the forces you have to the what? To the bottom. That is upward force equal what? Downward force. Yeah, let's go. What do we do? Now, who can tell me? I need someone to tell me which of these forces will be going upward. Now check. Can you tell me which force do you have that is directed upward? Now you will not be looking at C again. C that you have been broken into these two components. Yeah, now let someone tell me which force do you have to the top? Who can see any force to the top? Anyone? Who can see any force to the top? Just tell me what you see. Let's go. Anybody? Anybody? Look at this system. Look at the force that is pointing upward, this direction. Do anyone have an answer to that? Who have an answer to that? Oreoluwa, you? Are you? So let me start calling. Olumide, Deborah, Aisha, Amina, Esther, Constance, Divine, Vivian, Glory, Ifeoluwa, Joy, Mojisola, Masturo. How many of you like that? We have Oreoluwa again. We have Pleasure Ibrahim. We have Oyemumi. We have Favor. We have Nicholas. And we have Nadu Akir. Yes.
T is facing upwards.
Which one is facing up? Now we don't have T again. We have broken T into 3 components. I'm listening to 2 components rather. We are broken into T cos theta and into what? T sin theta. So which one of them is going?
T cos.
Exactly. T cos theta is the one going upward. You can see the direction upward. You know, I told you that the way this T point away, all these other ones too must point away. So I have T cos theta is going upward. Remember, upward force equal downward force is equals to W, the weight. So this one, let me help you write it there. So this one is what? Upward force. This one is what? Downward force. Exactly. Upward force equal downward force. So that's what? Your first equation. Second equation is this. Can you tell me which of these forces is going to the right? Which one is going to the left? So who can tell me which one is going to the right? Which one is going to the left? Anyone? Because I love to use this way a lot because it is the most simplest one for me. Yeah, let's go.
F is going to the right, while T sign is going to the left.
It's going to the left, exactly. So this one is what? The right one and the left force, exactly. They are going to be equal. Since the body is at equilibrium, they are going to be equal. And that is that about that. That is that about that. As simple as that. Very, very simple. Very, very simple. Very, very simple. Okay, let us look at this simple question based on what I've just explained now. So let's look at this question. We have a particular body here being acted upon by different forces. The particular force going here, another one is coming down, and we have this force going this way like this. So 3 Newton. This is 6 Newton. And this force going here is 12 Newton, making an angle that we don't know. The angle is theta. Ask it to find the value of theta. Option A, 15 degrees. Option B, 30 degrees. Option C, 45 degrees. And option D, 60 degrees. Can we attempt this? Exactly that same principle. Hello, I can use Lami's theorem, but that one will be too tedious for some people. Yes, my years of experience, like I've observed that people struggle a lot to use this Lami's theorem, but people can still comprehend triangular. But there are some people that don't even know how to draw this triangle. That's like another thing entirely. But this is always simple. This is always simple. So let us use this. Now pay attention. What do you do first? Come here and complete the triangle. Complete the triangle. Yes. Wherever your theta is facing, you call that sine theta. So this is 12. So you say 12 sine theta. And it's directed away. This other part for 12 cos theta is directed away. Exactly. Then we already know that upward force equal downward force. So it means that you can use anyone you like. If I like, I can use I can use any of this. Like I can use whether upward force equal downward force or side equal side. Anyone will give me my answer. I'm looking for theta. Okay, let me say upward force equal downward force now. I'll be using that small English. Upward force equal downward force. This is possible because this object is at equilibrium. Yeah, let's go. What's my upward force here? Who can tell me what's my upward force? Exactly what we are doing. What do you say?
12 cos theta.
12 cos theta, thank you very much. 12 cos equal to, what's my downward force here?
6 Newton.
6, exactly. Then what do? We divide this side by 12 to find cos theta. Cancel. 6 here 1, 6 here 2. How cos theta equal 1 over 2. I'll come here. Now, if I want to bring my theta to my cos to the other side, I will have theta equal half cos of 1 over 2. Now, the question is this. Okay, but look at what I explained at this side. When Joy asked the question about putting things in short form, then I told Joy to memorize all this. Now, everybody check. Cos 60 will give me 1 over 2. If I ask you, what cos of 1 over 2 will give me 60? What angle will it be? You can tell me. That is, cos of what angle will give me 1 over 2? Cos of what angle will give me 1 over 2? Who will tell me? 60 degrees, Abi. Exactly. It means that this thing I'm having here now, I'm having half cos of 1 over 2 is saying that what cos of what angle will give you 1 over 2? The answer is 60 degrees. And my answer is option D. Option D. As simple as that. But let me say now, pay attention. Let me say, okay. Let me say another person. Let me look for someone's name there. Let me say Nicholas now. Let me say Nicholas is not using upward force, downward force. Let me say Nicholas is using sum of force to the left equals sum of force to the right. So let us solve with Nicholas. So Nicholas is speaking this and this and equating them together. So I have 12 sin theta equals 6 root 3. So let's see if we get the same answer. I'll divide both sides by 12. So 6 here 1, 6 here 2. And I have sin theta equals square root of 3 over 2. If I bring my sign to this side, I have theta equal arc sine of square root of 3 over 2. Now let's go to our previous page. This is telling that sine of which angle will give you square root of 3 over 2. Now, come and look at this. Now check. Sine of what angle will give you square root of 3? Sine of what angle? Who can tell me that? What do you see here?
60.
Exactly. So my answer is still 60. So whichever one you are picking, you can see that this way is very, very simple. That is why I intentionally tell them. At times I'll teach this topic and I'll not even tell them what is Lamy's theorem. But some of them might be like, sir, let us solve something on Lamy's theorem. There's no problem. Let's look at something like this. You will see. Let's look at something like this. Don't worry, I will send the note to you. Just pay maximum attention. That's what you need in this class. Okay, look at something like this. So this is the last question, then I'll move on. They give it 30 degrees there. So they asked us to find the magnitude of force P. The magnitude of force P. They asked us to find the magnitude of force P. This is what they asked us to find. Okay, how do we get it? Pay attention. You see, let me tell you, you can still use that. Don't worry, method 1. Method 1. So if you can do that, you can rely on anyone. But let us always rely on the easiest one. On the easiest one, please. On the easiest one. Okay, so let me just use 2 methods. I can use more than 2. There are like 3 or many methods. Okay, let's go. Method 1 is we want to see how Lamy's theorem works. Lamy's theorem. Now pay attention. Let us find all these angles that we have here. Don't forget, this and this are perpendicular. So my angle here is 90 degrees. Let me use red color for that. My angle here is 90 degrees. Okay. Okay, I have 90 degrees. Now pay attention. This one also is 90 degrees. I have 90 degrees. Now pay attention. If this one is not, it means that the whole of the angle I'm having at this side like this now is 90 plus 30. Everybody check. 90 plus 30, and that's what? 120 degrees. So I have 120 degrees. So this angle here now, the angle between the forces, that's what you're looking for. This is 90 degrees. So everybody, sum of angle in a complete circle. Sum of angle in a complete circle. I'm coming. Let me admit some. Sum of angles in a complete circle is 360. So if this part is 120 and this part is 90, So what will be the other part? The other part will be 150, I think. If I'm wrong, correct me. This part will be 150 degrees, right? So if you sum up everything, you'll be having 360. Yes. Let me confirm that. That's 150 plus 90 plus 120. Exactly, that's it. So this is what I have. Now, according to Lamy's theorem, see, according to Lamy's theorem, by Lamy's theorem, I know that I will pick a force over the sine of angle that is facing it. Let us go back and revise that. I will pick a force F1 divided by sine of the angle that is facing it. Also, I'll pick a force F2, sine of the angle that is facing it, and a force F3, sine of the angle that is facing it. Exactly. So that's what we want to do now. Now let's go. This is a force 10 Newton over sine of the angle that is facing 10 Newton. That's sine 150. Then equal to, look at this force P that you are looking for. P divided by sine of angle facing it, sine 90. Then equal to, look at this one, F over sine of the angle that is facing it. Sine of angle that is facing F is what? 120. And I have 120 degrees. So the thing is that they just asked me to find P. They don't want me to find F. So which means this one, they don't want me to find it. So this is what I actually needed. So I can just use this one to solve directly. Yeah, let's solve with this one. What do? We have 10 divided by, everybody, what is sine 150? Do you know? Okay. We'll do some mathematics there. You know that, what is sine 150? Sine 150 is something as sine 30, but don't let me go into mathematics now. Sine 150 will give me half. Will give me half. That's 0.5 equal to P over sine 90 is 1. Sine 90 is 1. So if I divide anything by half, what does that mean? Like I'm saying 10 divided by 1 over 2 equal to P. Then remember primary school, when division change to multiplication, I will swap this to become 2 over 1. So my P is equal to what? 20 or 20 Newton. That is Lamy's theorem. But let me say, hey, some people don't know Lamy's theorem like me in this class. Some people don't know Lamy's theorem like me. And I only know what they taught us in this class, which is resolution like this, upward force, downward force. How do we solve this question? Okay, I will draw the diagram. Now, please check it out. Let me just draw it smaller here. I have 10 Newton. There's one that is going here, which is F. There's one that is going here, which is what? P. And I have one angle here, which is what? 30 degrees. Now, pay attention. Remember that they don't tell me to find F. I have no business with it. So it means that anything about the horizontal, let me just discard it. I needed something to the vertical. They don't ask me anything about this. So let me resolve this P to the vertical. Now pay attention. Remember how to resolve. I will still repeat that same word. Complete the triangle. Complete the triangle. Wherever your angle is facing, call that sine theta. So I'm having P sine theta. That is this one sine theta. And the other side, call it P cos theta. But I'm not using horizontal, I'm using vertical. Oh yeah, don't forget. Upward force equal downward force. Upward force equal downward force. Are we together? Yes, upward force equal downward. So my upward force is what? 10.
10.
Yes, my upward force is 10. Equal to my downward force is P sine theta. And my theta is what? 30 degrees. P sine 30 degrees. So I have 10 equal, sine 30 is 1 over 2. That's P times 1 over 2. So what I'm having here is like 10 equal to P over 2. And let me cross multiply. Therefore, my P will be equal to 10 times 2. That's 20 Newton. Whichever way you want to do this thing, we'll still get the same answer. Whichever way you want to do this, we'll still get the same answer. So I've given you these two methods. Just focus on these two methods, and to be sincere, you are good to go anywhere. You are good to go anywhere, and that's it. And that's it. Now, what do we now call this type of forces? If you observe these forces, observe that all of them pass through this common point. Look at this thing in green. Look at this thing I'm circling here. All of them pass through this common point. Even look at it. All of them. Look at this one. All of them pass through this common point. So what do we call the force that their line of action passed through a common point? What do we call the forces whose line of action pass through a common point? We call them what? Who knows? Who knows? Okay, let me give an option. If you know, you tell me. Okay, let me use collinear force. A collinear planar. Sorry. No. B concurrent. B concurrent. So what do we call it? Who can tell us? What do we have the word collinear? If I say forces are collinear, what does it mean? Who knows? Collinear. Break the word down.
On a line.
Use the smallest English possible. Co-link. Okay. Let me break it down. Co and line. This is what we join together to form collinear. So yeah, what are collinear forces?
Forces on a line, as in on the straight line.
Say it anyhow. You will make sense to me because I understand what you're saying. Tell me. That is forces that lie on the same line. Co is same. Forces that lie on the same line. Let me say I have F1 here, F2 here. These are collinear. They are on the same line. But what do we call concurrent? Concurrent are forces that they don't lie on the same line. These forces now, are they collinear? No, they are not on the same line. They are on different lines. But their line of action pass through a common point. So this type of forces is what we call concurrent forces. What do we call it?
Concurrent force.
Concurrent, exactly. That is, concurrent force, they are forces that their line of action pass through a common point. Or if you want to use simply, their line of action meet at a point. That is it. So that will call concurrent forces. Okay. What I used to round off this is, you see, we have some concept I want us to understand. What are those concepts? They are what we call, is about stability of body. It's about stability of body. Now pay attention. There are some times whereby a body will be in what we call stable equilibrium. Another body can be in what we call unstable equilibrium. Unstable equilibrium. And we can have what we call neutral equilibrium. And let us explain what. Some people. Okay, let's discuss this concept. When we say a body is in stable equilibrium, what do we say? This is when a body is in stable equilibrium. If the body receives a slight displacement, that is a slight push, it will return back to its original position. Let me give you an example. Look at this funnel. This is a funnel. I'm calling it. This is a funnel that I placed this way. This is a funnel placed this way like this. Everybody, look at this funnel. No, look at this funnel. Like the one that I have, like, look at the way I place this funnel. Everybody, look at this funnel. The way it is now, if I come here to give it a slight push, what happens? It will return back to its original position. So this type of or if I take a bow and I make it face this way like this, you observe that if you give it any slight push, it will return back to its original position. So we say a body is said to be in stable equilibrium if it returns to its original position when it is slightly displaced. When it is slightly displaced. Yes, that is it. And let me tell you something. Let me tell you something very, very important. You see, there's a particular condition, the condition that everybody check. For this object, the center of gravity is somewhere around here. The center of gravity is somewhere around here. If you observe something, you will see that the center of gravity is lower, that is lower to the ground. So a stable body have what we call a low center of gravity. That is, center of gravity is at the lowest point. That is why if you see two people fighting, most short people that fight, they are always very, very hard to take to the ground. I don't know if you have been involved in a fight with short person before, you will know. Those short people have what we call, they are very short, so their center of gravity is closer to the ground. Someone that is tall, it's very easy for you to just knock the person out very well. Someone that is tall, their center of gravity is very high away from the ground, so they are not that stable as short people. So that is that. So what do we call unstable equilibrium? Opposite of this. Everybody look at this funnel. Everybody look at this funnel. Look at it. This, even before it displaces it, it has fallen. It has fallen away. So a body here is said to be what? Unstable equilibrium. Unstable. This is what? Unstable. When you give this body a slight displacement, what happens? It's what? It will move further away from its original position. That's it. It will move away from where it was initially. This is what? Unstable equilibrium. So example is that if I say a funnel that is resting on the apex here, so it's unstable equilibrium. And what do we call neutral equilibrium? This is when if I have the funnel this way like this. Sorry, manage my diagram. If I have the funnel this way like this, that is the funnel is lying on the ground horizontally. Altogether, the funnel is lying horizontally like this on the ground. So the body is said to be in what? Neutral equilibrium. Why? Or check, if I place the funnel here, and if you push the funnel will tend to go and, when you slightly displace anybody in neutral equilibrium, it will go on, like it will come to rest again. That is the way it was initially, like this. Like that is the way it was initially. Like this. The way it was initially, like that is the way it is resting on a flat surface like this. Let me see how I can draw this thing. I'm coming. Let me see how it's been fine. Exactly. Everybody, look at the funnel resting on this surface like this. So if I push this funnel, what happens? It will roll and settle down the way it is on another new position. So this one is said to be what? Neutral equilibrium. This is said to be what? In neutral equilibrium. And then that is it. And that is it. That is it. That is it. Okay, so as simple as that. That's it. So as we've learned all this now, this is the end of this particular topic we are studying. So that's it. Do anyone have any question to ask? Do anyone have any question to ask? I'll wait for some seconds. Okay, if there's no question, let's all answer this question. Which of the following, look at this question, which of the following actions will increase the stability of a body? Now, this is the question now. Increasing base area. Raising the center of gravity. Raising the center of gravity. Lowering the center of gravity of the body. So look at the question. Now, pay attention. Option A, you have it to be I and II. Option B, you have to be I and I. Option C, you have to be I and I. Option D, you have to be I and I. Did like all of the above. The severity of the following actions will increase the stability of the body, increasing the base area, raising the center of gravity, lowering the center of gravity of the body. So what's the answer? A, B, C, or D. So pick your answer.
A.
Okay, so
Sir,
some
B.
people choose A, some people choose B. Okay. If you don't feel like talking, maybe you don't want us to hear, but you can type on the chat box. I'll see it. You can
B.
type on. Okay. I can hear from Asura.
A.
Okay, I can hear from Divine. I can hear from Q.
B.
3 people have talked so far out of 21 students. Okay, let me wait a little. Let me just wait some seconds. Okay, yeah. Favor, you are raising your hand. Okay, let's hear from you. What's the correct answer? Which of the following will increase the stability of the body? Is it by increasing the base area, by lowering the center of gravity, or by raising the center of gravity? So, Favor, I can hear you. What's the answer? Unmute yourself so we can hear you.
B.
Yes, Vivian, talk. I can hear you. What's the answer?
A.
Sir, B.
Okay, who said A? Who said it? Okay, Esther, what's the answer?
A.
A, okay. Esther, you chose A. Okay, some people chose A and B. Okay, the answer is between A and B. All right, let me discuss it. Pay attention. Okay, pay attention. No. Number one is increasing base area. Of course, yes. Let me tell you something. If I ask us, which of these two bodies is stable? Which of these two bodies is stable? You have a body staying this way. You have a body staying this way like this. And you have a body staying this way. You have a body staying this way. Now, look and tell me now. Look at these two bodies. Let me say A and B. Which of them is stable? Which of them is a stable equilibrium?
A is stable. A is stable.
How do you know? If guys, everybody will know. So A is stable. Why? If you observe the base area, I have a more higher base area. I mean, I have higher base area. Good base area. Thank you. Why this smaller base area? So this is unstable. This unstable. So this thing. So this one is clear. Now the next one they said is that increasing, what they say, raising the center of gravity. I'll still use the same example. Everybody check. Remember what I told you about short people? And I use this as an example that a stable object, see, look at this guy, look at the center of gravity somewhere here. And look at this one, look at the center of gravity. This one has higher center, this center of gravity here is raised. It's like a raised center of gravity. And this one is what? Lowered center of gravity. So if you have an object that was the center of gravity is lower, the object will be very stable. Now look at this. So what's our answer? So look at this one now. The center of gravity is somewhere around here. There's an advanced way of finding center of gravity, but that's not our way. That's not what we are doing. But the center of gravity here will be that if you want to spin object like this, you observe that this is where you want to put your hand. Yes. So this one have lower center of gravity, but look at this one now. Has higher center of gravity. So therefore, number 2 is wrong. If you raise the center of gravity, the body will be what? Unstable. So if you want, so the lower the center of gravity, the body will be stable. So our answer is what? Option B. So thanks for those that attempts. I like that. Nice one. You are doing well. Nice one. You are doing well. Okay. So that is that about that. All right, that's that about that. So we are done with this particular topic. So guys, we should move to the next topic, or you stop here.
Move to the next topic.
Next topic. Okay. Our next topic, so is what we'll be able to finish within short time. It's not something complex. It's more simpler than this other one. And what we want to look at is what we call elasticity. That's elasticity and Hooke's law. Okay, I want to stop this particular recording for this topic. Then I'm coming. Just give me some seconds.